Tonight we're going to be looking over one of our local teams that are pretty near us, Vector 8177. So they're an open alliance team, so they've been sharing their CAD and the progress of their season the entire time, and we've competed with them a couple times this season as well. Um, they had a robot that was pretty similar to X-Ray, but one of the reasons why I wanted to look at it was it's also different in a variety of ways. So seeing how another team built a similar robot to us and seeing some of the differences should be useful so we can see how we could have chosen to do things um, if we did things, if we had decided to do something a different way. Um, so in terms of like the mechanisms, they're pretty similar. They have a MK4I swerve drive base 2 um, with a metal belly pan, same type of 2x1s connecting everything across. Um, Versions of our Spectrum corners, I'm pretty sure this is actually modeled directly off of our 2022 ones. Um, so a very similar drive base. Um, but things start getting different when you start seeing just some of the dimensions and things on the robot. So if we look over, they're 26 by 26, so they're a square, where our robot was like 24 by 27, 24 and a half by 27 and a half, something like that. Um, so they're a little bit different, and they have a little bit more width to them, so about 2 inches wider and about an inch shorter in length. So that does determine your wheelbase a little bit, so that means you're probably a little bit more stable from tipping over side to side, but slightly less stable tipping over forward backwards. There is some benefit to building even bigger, especially if you have a game where you have to reach up very high and where you might get pushed around at that same time. So especially a game like 2019, where you have to reach up to the rocket and score on like the high goals of the rocket, which was like 8 something feet in the air, and you had a defender that was possibly pushing into you. Having a much wider frame um, can be beneficial there, so you never get tipped over. Anything else you can do to keep weight down is always helpful, because that helps you not tip too. Um, the rest of their drive base is kind of built on what looks to be this main center pillar. So they're able to have this crossbar here that runs across their belly pan and separates where they have the battery. So they ended up putting the battery up front compared to ours, where we have the battery in the back. And then they have the rest of their electrical under this, what looks to be like electronics cover, and most of their main control system stuff, the Robo Rio, power distribution, all of that is on this side of that bar. Looking at it, yeah, it doesn't seem like they have any wire pass-throughs up to here or anything, so they're just going to run everything like over the center, so the battery cable probably just gets run over the center here. Likely with the lead sticking up, because otherwise they'd be hitting these posts here. In some way for a battery strap. I think this is a similar way that like the Kitbot chassis does the battery strap right here. That 26-inch width, one of the advantages of that is you can get the battery between two rails that run the whole length of your robot. This is basically the 2 inches that we remove from ours by having a 24-inch robot. And so the motors get a lot closer, and you can't really have these rails here if you do it to the width that we have been recently. So it's one of the thoughts is to go a little bit wider. It makes it harder for us since our laser cutter is the way it is. We can't laser cut our own belly pan if we do that, but we have sponsors who can laser cut belly pans, or we could route our belly pan if we needed to make it wider, or do the belly pan in 2 parts. So this gets fully gusseted. It doesn't look like it's mounted. Oh yeah, so it's mounted just on the center row right here to the belly pan, and then the gussets to the side rails, and then these big structural gussets up to the uprights that support the elevator. And then the back end of their elevator is supported by a 2x1 cross beam, relatively similar to us, just going on top of their swerve modules. But they ended up doing it just by having the tube blocks here. So they have the bolts into The end cap or the tube end nut, if we hide that briefly, we can see the block inside of here. So these are the West Coast product blocks. So they fit inside with like a 3D printed exterior to fill the little gap, so you can use different size tubes. And then they just bolt everything into that. And so that's how they support their elevator across the back with slightly different 3D printed covers than what we were running, where they just cover up the main motor gear set on the MK4i. But theirs seem to leave the belt exposed, so they can get in and probably do maintenance on it and things. And that still lets you grease the gears from underneath if you needed to, without having to take it off or anything like that. All right, let's see. So going up, this is a relatively, let me get rid of some of this covering to make it easier to see everything. We're just going to hide some Deluxan panels. So the elevator looks pretty stock. So they were actually using at least some parts from the Thrifty Bot elevator. So there's different commercial off-the-shelf elevators you can buy from the different vendors. So like the Thrifty Bot has one, West Coast Products has one. Andy Mark has some different parts of an elevator, so does Rev. And so you can, a lot of teams ended up kind of combining them to make the various elevator parts that they wanted to. So they seem to be using the Thrifty Bot mounting bracket. So these let you mount the elevator chain to your tube. So these are nice big chunks of either aluminum or steel. I don't remember right now. But they're large and are spaced right for you to be able to put the threads through your number 25 chain and just bolt directly to it. So instead of us having that like belt that goes through the whole elevator, they have these 2 loops of chain that power their first stage. So as they move the chain rail, or they move this chain up, the this stage of the elevator goes up and just gets powered directly by that. They're also using West Coast Products bearing blocks. Oops, swerved around too much. Hold on. Okay. So these little bearing blocks here are the West Coast Products clamping blocks that go on like the outside. And so I believe these like, yeah, so these like bolt all the way through. And then the inside bearing is on the block in here, like that. So you end up with a pretty small inside bearing, similar to what we had as well. I think they're like 1/2 inch diameter. I think they end up being half. It says it's a little smaller. It might even be a little smaller. But so that's what the bearings ride on. But this allows you to very easily use it with pretty much any tube. You can drill the holes yourself into tube, or you can use like the Rev tube or any of the pre-drilled tube, and bolt all the way through onto the block. So instead of ours that bolted on the inside face, these clamp around the outside. And either of them still end up with a pretty large gap here between the tube rails, which sometimes can be a problem, but is also a lot of times fine. Like most teams can get away with it without too much of an issue. Some teams use it for things depending on how they rig their elevator. Maybe easier to get string that runs like inside the rails or belt or anything between it. The rest of their elevator, they use the tube plugs again, the same place that they mounted over here. There's tube plugs mounted everywhere inside these joints, so they don't have any external gussets. So there's not gussets running along these outsides anywhere. And if you had different bearing blocks, you might need them, but instead they're able to just bolt to the inside here. So no gussets. Just kind of changes how you have to have your strength. So all of it has to come from just these bolted connections. Most of the time is fine. I imagine they didn't have these wide flange bolts everywhere as they seem to intersect here. They probably just used regular bolts, or at least on the middle one. To actually power the elevator, we have Neos into max planetaries, into, let's see, if we remove this cover, into what looks to be just a 1-to-1 gear reduction. So this was basically to be able to flip the motors around, not have them sticking out this side at all and like overhanging. They just have this gear reduction, or this, not even gear reduction, just these two gears here to just transfer the power here. Doing it with gears is fine. You could have also done the same thing with chain if you wanted to, possibly even belt if you had large enough pulleys. You could have done it with belt. It would have been a little bit thicker probably. It also means that if you have to change something up here, you don't have to like take the motor off to do it. You're not direct driving the shaft. It gives you a bit more versatility. If you needed to, you could possibly change this gear ratio. There's probably gears a little bit bigger than that. Let's see, that gear actually. Yeah, so it's only 56, so you could potentially make this gear bigger, make this gear a little smaller, and actually get a little bit of a bigger gear ratio, or go the other way if you wanted a little bit more speed. It might change how the covers and stuff work, but you could definitely do a little bit of configuring after the fact, after you build everything. If you wanted to change your elevator speed a little bit, you could slow it down or speed it up by replacing these gears on both sides, in case you wanted to go a little bit more finer detail than you could get with just the max planetary here. Because the max planetary only has certain stages you can use, right? So if this is 2-stage, this is probably 3 and 3. For like 9-to-1, I don't know what it actually is, or if it's even configured to anything. Yeah, it's configured 9-to-1. So that's probably what they used in real life. Anything too much faster than that, or bigger than that, gets you a pretty slow elevator. And then if you go down to 1 stage, you can only get to 5-to-1. So you have a pretty big gap in your reductions. We ran into the same thing. You're either at 9-to-1 or 5-to-1. So having this gear reduction out here does allow you to tune it a little bit more, which is nice. Let's see. So they have the rev through bore encoder. So this gives them an absolute encoder on this shaft. So they can use a little bit more precision in knowing where this shaft is when it's turning. Which is sometimes useful. You have to feed that back in either to the Spark Max or to the Rio directly. You also don't have any backlash from the gears or anything. So instead of like sensing where the motor is, you're sensing directly where this shaft and sprocket are. So it probably gets you a little bit more precision on exactly which height your elevator's at. What did we discuss? Okay, so we talked about the first stage of the elevator going up, powered by the chain. And so when you do this, when you have this like continuous loop of chain here on your first stage, this signals that you're going to be using the elevator rigging known as cascade. So on X-ray, when we looked at that, we had that one long snaking belt that went through all of the different stages and got attached to the carriage at the end. So that's continuous, because you have one motion thing, either chain or belt or string, going up all of your stages and ending at the carriage, and then getting pulled down back to your motor setup. In Cascade, you basically move each stage independently, or you move your first stage independently, and then you basically tie your next stage to the motion of that first stage. Let me separate these. Do something different. Hold on. There we go. Okay. So in CAD, it's a little weird sometimes. It doesn't always let you move it exactly how it moves in real life. But in real life, for every inch that this first stage goes up or down, this second stage will go up or down as well. So as this moves up like 5 inches, this one moves up 5 inches from this stage. And so those are always like connected together. Get that to where it's not hitting it. Okay. And so you can never have like, there's some positions that you can put into CAD that when you're in a cascade rigged elevator, you can't actually do in real life. So let's see if I can get one. So with this first stage all the way down and the carriage stage all the way up, you can't actually do this on a actual cascade elevator because they're tied together. So this, if this first stage is all the way down, the carriage is going to be all the way down too. And if they're both all the way up, they're both going to be all the way up together. And And if one's in the middle, the other is going to be in the middle as well. It's tricky to figure out. I think you have to like bring that to middle and then this to middle. Yeah, something like that. So like to get them both in the middle, it would end up about there is what it would look like when they're actually driving. And so the way they tie them together is with some string. So that's what these pulleys are for. They do them on each side to keep everything balanced, so you don't have any like angling, so you don't have like this side getting pulled up faster than this other side. That's why you have this chain on both sides too. It keeps everything kind of balanced and nice. There's some redundancy if something were to like happen to one of these chains or to one of the strings. The elevator probably still works a little bit. It's not great. You don't want to fix it after the match, but you can still move it up and down most of the time and probably still score, which is nice to have built in. So the string down here gets tied around and goes up to that pulley, and they're tied in different places. So the string is mounted into these plates on this back bar. So this bit of string doesn't move. It's completely fixed and attached to this bar. And then the ends of the string are attached into these mounting points that are sort of cammed, or even if they're, I don't actually think they're cammed, I think they're just tight. So they're able to pull these tight and tighten these up and like wrap the string around it. And that holds the ends of the string in place and allows you to tension them. And then since it's fixed at the ends and it's fixed here in the middle, it basically forces this to move up to the top when this part is moved towards the bottom. And so it's like the displacement between these two positions that is changing as it's moving up and down. And so this works with multiple stages. You could keep going. This has 2 moving stages, but you could have 3 or 4, and you could build this same setup into all of them. Continuous and Cascade do, most of the time they do the similar things. If for some reason you needed to have a setup where you could put the carriage at the top first, you can't do that with Cascade. If you really needed your robot to be able to be in this position, where you have this all the way down and this all the way up, Cascade wouldn't work. So some teams did that in like 2018 when they wanted to be able to have their intake like score over the top of their elevator. You couldn't do that with Cascade. Most of the time that's not a big deal. In games like this, you probably didn't need to flip your intake over the top of your elevator. So you weren't really worried about it. But in previous games, sometimes it mattered. The other thing that Cascade actually does help you with is you end up getting a bit of a speed advantage, because whatever you're driving out here, whatever gear reduction is out here when you're spinning this up and down, you actually double that at your carriage. So you double the speed at the carriage. So you end up having to have a little bit more reduction on your motors, or to have a smaller pulley here, to be able to move it up and down and still be controllable. And so if this is moving at twice the speed of the outer section, since that for every inch this moves, this also moves an inch, which ends up giving us 2 inches total when they combine. A lot of teams will use this in previous games to be able to like mount hooks up here for like a climbing mechanism. So you can have more torque here, so you're able to lift more when this section pulls down than you would if you mounted your hooks on your carriage segment of your elevator instead of the Cascade first stage. So because those two things are moving at different rates, you can use that to your advantage sometimes depending on the game and what you're trying to do. In this game, didn't really matter either way. There were a lot of teams who had very good Cascade elevators. There were a lot of teams who had very good continuous elevators. Some of it is just which way you feel comfortable building. In the past, we had done mostly Cascade. We decided to do continuous this year, just because of how we wanted to package things. But we could have easily done something Cascade as well. what do we not talk about? They have their gussets up here that mount their fixed back rail. Also has the bearings in place for the top of their sprockets. So that setup's very clean and easy to potentially copy. So if you had to build an elevator, this is a very nice, clean way to do it. It does look like, I believe this is the Thrifty Bot spool. I think we actually own one of these. And this is for a, not spool, this is the holder for a constant force spring. So a big constant force spring gets attached to the carriage here and helps lift the whole assembly. And so that takes some of the load off your motors, allows everything to move a little bit faster and easier since your motors aren't having to lift everything and fight gravity all the time. They're just fighting to actually move the system, not necessarily to push all of it up against gravity. The spring's doing a lot of that. So it's moving a lot less weight. Okay. I think that's most of the elevator. Similar to X-Ray, they had a wrist, but instead of a 4-bar, they just had a normal pivoting shaft. So their wrist was this mechanism out here. They have a Neo with a max planetary and a max planetary 90 that they use to get sprockets on both sides. Hard to elevate it. Yeah, it doesn't look like we can quite get that to be hidden as easily. Oh, I can bring it up to the top. Let's do that. And bring it out of the gusset so we can see it a little cleaner. Okay, so let's see how they mounted some things into this. So they ended up having what looked to be probably 3D printed spacers here. And then likely, I'm not really sure how they mounted that. Somehow they mounted into that plate. It looks like they're catted as just rivets. Let's see if I hide this. Yeah, it doesn't show anything going into here, but my guess is these bolts are actually just bolts long enough to bolt through and into the max planetary mounting in here. That would be my guess. Let's see, to do it on the other side? No. Okay. So otherwise you have to have some way to mount it, and there's no easy way to mount from the inside out anywhere. So it's probably bolts going in through the spacer and just locking everything in place there. And that's mostly just holding your, that's not really doing too much structural, that's just holding the motor and stopping it from like rotating while it's trying to spin the actual arm and everything. Because you do have you have the crossbar of the actual carriages kind of holding everything apart. Oh, even more so, these plates, that's interesting. So these plates were actually designed with a bend in them. At least what it looks like. Yeah, so you get a lot of strength there when you have this full aluminum gusset that's even bent down and attaching to this lower rail. It would be very hard for this to deform too much. Let's see. Yeah, so it's just an 1/8 inch aluminum plate that attaches everywhere, supports the bearing, or supports the shaft at least, with bushing. So they ran with the likely Thrifty Bot, possibly West Coast. Probably tell us. Yeah, Thrifty Bot bushing. So instead of a bearing where you have the rollers that actually spin, these just spin the bushing, or spin in the bushing and just kind of like rub against it. And they're just made of Delrin, so they're smooth, slick plastic that reduces friction. So anything that's not going to be spinning very fast, this totally works for. And the wrist is not going to be continuously rotating, so it's never going to be spinning all that quickly. You're only going to do that kind of pretty short motion in and out with it. And so that should work just fine to have a bushing there and not a bearing. Again, it looks like they just have them on these outside plates, which is fine. You don't really need them on the inside. You already have the bearings in the actual Max 90 supporting the shaft, which should be plenty. up here, we see how they actually mounted their arm itself. And so looking at this, what do we see? So we have the two sprockets that are driven by the smaller sprockets in the back. And it looks like they're mounted to hex hubs here. So these are Vex Pro hex hubs to something, yeah, chainring bushings, probably Andy Mark sprockets from the look of it. And so these are directly mounting and spinning the hex. So they're transferring the torque of the wrist through the hex shaft. And then they have these 3D printed parts here that are acting as their hex hubs for the intake arms. So you have these large 3D printed parts in addition to, oh yeah, so yeah, they don't even have the 3D, the polycarb part doesn't have a hex in it at all, it's just round. And so you're just transferring all that torque through these printed parts. They have nice big 3D printed parts, so they're not gonna break easily or anything. They did the embedded nuts, so they push the nuts inside of there so that they can bolt into it. And there's a very long part of the hex in here, so it's really hard to round that out. You have to push through a lot of filament to round this out completely. Not impossible, but pretty difficult. And since there's not a ton of load on it, just the wrist, and you have it on both sides, it's probably fine to do it that way. Again, they have the bushings up here to support the rotation of the shaft, and they also embedded one of the rev through bore encoders so they can know the exact position of their wrist without having to do the zeroing or anything from the motor encoder. They have the sensor here to be able to tell them exactly where this is tuned to. Even if they start it in a different position than normal, it should know its angle directly and be able to tell you where it's moved to. All right, so what's the last thing? So they do have a little camera mount for their driver camera. So this lets them see the intake at all times. So if they're going up and getting from the feeder station or anything, they can see if they're ground intaking or scoring. They have that camera view for their drivers. And then the last part of this robot is the intake, which is, yeah, so 6mm, 1/4 inch polycarb, 0.22, which is that kind of standard-ish size, polycarb size. Gap is, didn't get gap, got surface area. Gap is 13.5 inches, so plenty of room for the cube. And then the cone comes in through these rollers here. Let's see how they did power transfer. So they did power through the outside, so the Neo mounted directly to the plate, and they go belt to the hex shaft, that then goes through the inside roller, their back roller. It's powered all the way through. And then these two front rollers have to be spinning in different directions. So, and actually this bottom specific one has to be spinning opposite of these other two because they want to be able to suck the cone in between these two and the cube in between these two. So it's okay if these are spinning in the same direction, but you need this one to be spinning opposite. So they do that by having the belt here connecting these together. So these are spinning the same direction because the belts don't flip direction when you power transfer. And then on the opposite side, they have a gear setup that gets them the ability to flip the direction because the gears do flip direction. And then they have another belt that comes up and powers this front roller so they can have the counter rotating rollers that they need to suck in the cone or the cube. What else do they do? So they have these additional little bearing plate out here so that they have this intermediate shaft right here for this gear and pulley being able to be supported by two different bearings. So they have one in this exterior plate and then one on the interior plate. In CAD, they ended up having this shaft has a lot of bearings on it. It doesn't necessarily need to. I guess it only has 3, so it's probably fine. With the distance that it is here, there's no issue in supporting it with 2 bearings here. If you didn't, you could possibly see some deflection between the gears. You probably would get away with just having the shaft end here right at the end of this bearing, at the end of this gear if you wanted to. But having the extra bearing doesn't really hurt you in any way. In most things, especially when it's just mounted into the plastic with bolts, it's going to kind of self-align. It's not going to cause any binding or anything like that, unlikely. Let's see. Yeah, all of their shafts are just powered hex shafts in rounded hex bearings, most likely, and then they just have the tapped ends with bolts, which we're probably going to use a little bit more next year. It's super fast. We can just cut the shaft, tap it to 1032, put these bolts that already have the large washers on them to secure it so you can't pull it through the bearing. And so it's nice and easy to make roller shafts quickly. It does mean that taking them off can be a little annoying sometimes, depending on how you get them through the plate. So like this back shaft, if you had to change it, is a little complicated because you have to take out the bolt from this end and basically push the shaft all the way through the other end. So if you needed to like replace one of these interior wheels, it does take a bit. You have to drop everything out, slide the new wheel on, then push everything back on, get it all aligned and set up. You can't just like pull the roller and replace it. So there's some things you can do to improve that, but it also means everything's going to stay together nicely and be mounted very securely, which is good, even if maintenance takes slightly longer. Yeah, they do have the standoffs back here to stop the cube from going back out of the intake. I don't actually know what they're doing here. So this looks like to be a 3D printed part that is either stopping the cone from going in at a weird angle or stopping the cube from touching this roller, probably. Because you wouldn't want the cube trying to like force its way out of this small gap as this is intaking in. If this is spinning, yeah, because if this is spinning this way, that means this is spinning the opposite way. So the cube could try to like force its way out. So it's likely that these parts are there to stop the cube from trying to do that. That would be my guess, at least. That's a pretty good use of a 3D printed part. You can get that nice, weird, kind of sloped concave angle there that would be really hard to make any other way. Very easy just to bolt that into the plate. You can add a little bit to stop it from rotating up at the top of the plate. So it's a very easy use of 3D printing. And they just have a little connector piece here so that they can make these into 2 separate segments to make it even easier to print. You don't have to have a super long or super large printer to print this all as one piece. Just do it as 2 and then bolt it together here in the middle. Let's see what else. Oh, we have another 3D printed part here. So they have a limelight mount they made. That's another just printed part. Lets them print it nice and easily at the angle they need. And then just bolt it to a piece that's already flat. So this would be a pretty easy thing to print. Shouldn't need support or anything. It's just going to print with this on the bottom and go straight up. And you get the angle very cleanly. You get nice places for bolts. And then bolts and zip ties, or bolts or zip ties for your limelight. Very easy construction there to be able to set an angle exactly like you need to find that all in space for your vision processing or anything else you need. think that's most everything on this robot. The other really nice thing, we already talked about their polycarb covers. We didn't talk about the other covers on this robot. If I can get back to, let's go back to the beginning. Let's use on-shape version. I can just go back to start. So we can see their covers. So they do have a lot of bent polycarbon things to stop anything from falling into the robot. It also just makes their robot look really slick and clean. Right, they keep all the edges lined up with their gearbox covers here that are printed. And so they just do all that with standoffs coming off their rails. So they have a few hex standoffs here. There's ones coming off the tube in here. So that's not too bad, and it was pretty easy to do. I think it's all just eighth. Yeah, so it's all just eighth polycarb that they bend up and around. They can put all their sponsor stickers and labeling and team labeling on it. And it makes for a very clean external package. It makes it very hard to get any game pieces stuck in their robot. And relatively easy just to pull a few bolts to take it off to do maintenance or work on it. Nothing too complicated there. Yeah, overall, it's very nice, well-designed systems in place. The intake was able to go down and get floor cones and cubes. Yeah, somehow in there, once the bumpers aren't, yeah, when you have the bumpers and everything and you get the cutouts and you can actually get the intake to move correctly, which Onshape doesn't want to do right now. But they were able to iterate throughout the season and make a lot of different things work and have a pretty successful year. All right, I think that's the end.